Hello, this is section 2.13, and today we're going to be talking about um, lone pairs of electrons, the non-bonding electrons, and we're going to be talking about them in in the in the context of either being localized onto an atom or delocalized in between atoms. So what does this mean? So if we go back to section 1.8 in oh wait, no, that's not 1.8. If we go back to in our book, section 1.10 in predicting molecular geometry and V-separator theory, what we remember is that if you have some molecule like this, the nitrogen has a trigonal pyramidal geometry, and the lone pair sits in an sp3 orbital because the nitrogen is sp3 hybridized, and the lone pair is totally localized onto that nitrogen. Totally localized means that the lone pair has 100% spent its time in an orbital of the nitrogen atom. And while that sounds like a weird thing to say, there are cases when a lone pair would not be always on the nitrogen atom. In fact, we have seen some examples like this, where in this molecule, the oxygen has two bonds and two lone pairs, which means it's formally neutral, right? And if you take the geometry of those four groups into consideration, the oxygen has an sp3 hybridized tetrahedral arrangement. However, there's a very good resonance structure that you can make where one of the lone pairs comes down to fulfill an octet, putting a positive charge on the oxygen, which isn't always great, but now they all have full octets, and there's a big change that happened in the geometry of this oxygen, because before it was sp3, if you remember, and now the oxygen has an sp2 hybridized geometry around its atom. Also, the lone pair that we're talking about here is in an sp2 hybridized orbital as well. It is also localized onto that oxygen. Another case that does not have localization, where it is localized, is one best described like this. So the most classic example of very good delocalization, we'll just have this like a hydrogen there, comes from an amide type functional group. So in an amide, you can have electrons that flow down in between the nitrogen and carbon, and then electrons from the double bond flow up to the oxygen. To give you a structure that looks like this. You've seen me draw these a few times in recent lectures because it's such a good example. And so this molecule is particularly interesting in its resonance form because, I'll just redraw these here. There we are. Because since the lone pair can participate in a resonance form, the lone pair isn't totally on the nitrogen. If you remember from the last section, 2.12, we drew a resonance hybrid of this molecule. where the oxygen had a partial negative and the nitrogen had a partial positive. If the nitrogen has a partial positive, that means the lone pair is not really acting like that fourth group that makes the nitrogen sp3 hybridized. Now it's more acting like the sp2 hybridized nitrogen, and it is acting as if it is in a double bond with carbon, which means that carbon is also sharing some of um, that electron density with the nitrogen. So because we can draw a resonance form with the lone pair, we would call that lone pair delocalized into some overall system that is conjugated. And it has to be conjugated so that you can make a resonance form with it. So that would be the rule I would say to remember. If you can draw a resonance structure, a lone pair is delocalized. I would say that's a pretty decent rule to follow. And that's basically what 2.13 is trying to tell you. Just trying to have an idea of what makes something localized or delocalized. And this has been section 2.13.